Faraday's law of induction. Michael Faraday and Joseph Henry showed that a changing current in one loop induces an EMF in a second loop. The changing current in the first loop creates a changing magnetic field. What is actually causing the EMF is the changing magnetic flux, not just the changing magnetic field in the second loop. Faraday's law of induction states that the induced EMF in a wire loop is proportional to the rate of change of magnetic flux through the loop. This equation for induced EMF is on the AP2 equation sheet. Michael Faraday made some of the greatest contributions to physics in history, focusing on electricity and magnetism and their interactions. Albert Einstein kept a picture of him, along with pictures of Sir Isaac Newton and James Clerk Maxwell in his study. Michael Faraday only had a basic education and no mathematical training beyond basic trigonometry. He had fantastic vision and scientific creativity and was a superb experimentalist. It remained for Maxwell to put a mathematical formalism behind Faraday's concepts. Faraday came up with the concept of the existence of a field generating a force to explain electromagnetism. The field theory was then taken up by Maxwell and is used extensively by physicists to help explain quantum mechanics. Delta phi sub b is the change of the magnetic flux. Something has to change. Remember, the formula for magnetic flux is Ba cosine theta. If any of these things change, you will have change in flux. So either the area of the loop changes, the angle that the area vector makes with the field, and or the strength of the magnetic field. If any of those change, then you get a change in flux. Delta t is the time interval over which the flux is changing. The negative sign is related to the direction of the induced EMF and will be discussed later. For now, we'll focus on the magnitude of the induced EMF and work an example problem. Find the magnitude of the induced EMF in an 8 square meter one-loop coil when it is perpendicular to a 0.4 Tesla magnetic field that decreases to 0 Tesla over a time interval of 2 seconds. All right, so we have an initial field, we have a final magnetic field of 0 Tesla, we have a time interval of 2 seconds, we have an area of loop of 8 square meters. So the initial flux is 3.2 Webers. The final flux is 0 Webers because we have 0 field. Therefore, the change in flux is negative 3.2 Webers, but we're going to ignore that negative sign for now. We're just going to worry about the magnitudes. We have absolute value signs here. So the change is 3.2 Webers. The time over which that change happens is 2 seconds. Therefore, we have an EMF of 1.6 volts. It's as though that loop has a battery connected to it of 1.6 volts, right? So you're going to get a current due to that voltage there. So far, we've dealt with the magnetic flux changing due to the magnetic field increasing or decreasing. But how does the area of a loop change? Consider the case below, where a mechanical force, someone's hands, acts on the wire loop. So here, if you stretch this loop out, the flux is decreased because the area was decreased, right? So you have less X's in this loop than in that loop. Another situation where the area can be considered to be increasing or decreasing is if a loop is entering or exiting a uniform magnetic field, as shown below. This situation arises quite often in this course. So we have a loop and it moves with velocity into a field. So the more magnetic field lines that go through the square loop of wire, the more flux. So the area of the loop that is in the uniform magnetic field is increasing. So as it goes in here, so here if you move the square over here, then all of a sudden we have 3 X's in it. As it keeps moving, you're going to get 4 X's in the loop. So technically, this counts as the area changing because really it's just the area that has the field in it. Here, none of the area had the field in it, and then here, all of the area has the field in it. So you can see that that area is changing as the loop moves. Once the loop is completely inside the field, the area of the loop in the uniform magnetic field does not change. So therefore, once the loop's in the field, even though it's moving here, it won't have any flux because that won't be changing. The amount of magnetic field lines going through the loop will not be changing once the loop is entirely inside the field. Magnetic flux also changes if the angle between the loop and the field changes. The loop below is rotated from being perpendicular to the field to parallel to the field. So you can see that here we have maximum flux because the field lines are going straight through the loop. Over here we have zero flux because the loop is parallel to the field. However, a loop spinning in a circle as shown about this axis here in a circle will have no change in flux. The loop spinning about its center of mass will have no change in the number of magnetic field lines going through it. There is another way to solve this problem if either the magnetic field or the cross-sectional area of the loop is constant. Remember, induced EMF is change in flux over time. Change in flux is final flux minus initial flux. That's still all just divided by time. What is flux but B times A? And in this case, we're assuming that the loop is just going to be perpendicular to the field. So that's why we don't have cosine in here. So BA final minus BA initial. If the magnetic field is changing and the area stays constant, then that means A final equals A initial. We can factor out A to the front, and then it's just A times change in magnetic field over time. If the magnetic field is staying constant and the area is changing, we then have that B final equals B initial. So we can actually factor out the B, and then it just becomes B times change in area over time. What if the magnetic field and area are both constant and the angle between the loop and the field is changing? Well, just use your version of the equation, BA cosine theta, and we end up with BA times the change in cosine theta over time. But be careful, this equation calls for the change in cosine theta, not the change in theta. If there's more than one loop of wire, as shown here in a solenoid, you just multiply the result by n, the number of loops. So this equation becomes this equation. You just put an n in there. Only this version, without the n, is included on the AP Physics 2 equation sheet. You just need to know that you can multiply by the number of loops when there's more than one loop. So if you have two loops, you end up with twice the induced EMF.